right, so we're going to jump around a little bit. I think we kind of left off. We had started talking about bias in our sample through cluster or stratified random sampling. We can kind of get our sample to match up more with our population. Instead of talking about bias, I think I'm going to save that discussion for when we come back from spring break. I think it's a good one to kind of start out with. And we can kind of get through a concept here today and Friday before we leave for a week. So up to this point, we've talked about the distribution of some continuous random variable. It was almost like we were looking at the population data, right? So now we're going to think a little bit differently, which is what's the distribution, not of the variable that we're looking at, but what is the distribution of sample means? Okay. So you can imagine, let's say I'm interested in the average, income in the US. Right? And maybe I take a sample of 100 people and I calculate the sample mean from that 100 people, right? The average income. I write that number down. I randomly sample another 100 people. Calculate the sample mean for those 100 people, write that sample mean down. I keep on doing this, right? So maybe I do this 1,000 times. So I have 1,000 different sample means. We can imagine if I had 1,000 different sample means stored in Excel, I could pretty easily find the mean of those sample means. I could find the variance of those sample means. I could even look at the distribution. Right? So that's what we're going to be looking at today. So I'll kind of start out giving you some statements. And then instead of looking at mathematical proofs, I'll try to kind of support what I'm telling you with data. Okay? So the sample mean will have its own distribution. What's also going to be true is that the sample size that we take, every single sample size will have a different distribution. You can imagine, let's say I'm thinking about average income. Let's say I start taking samples of size 1. So if I randomly select one person, right, I could see a sample mean out there. It's kind of weird to talk about, but a sample mean from one person is just whatever that person's value is for their income. So maybe I randomly select one person, I see they make 33,000. I randomly select another person, they make 60. I randomly select someone else, they make 150. Someone else 80. Another person 250,000. You can see a pretty wide range of values. However, if I take samples of size 10, or let's say 100, right? Well, even if I take samples of size 100, if I end up with one person who makes 250,000, it's only going to be one person out of 100, right? So it'll pull on that sample mean a little bit, but I won't be able to see, across 100 people, it's very unlikely I see a sample mean of 250,000. So the higher the sample size I take, the extreme values are less likely for me to see. The other example I sometimes use is height, right? If I'm just taking samples of size 2, and I end up with someone in my sample who's, 7'2", well, that's going to give me a really high sample mean. But if I'm looking at 100 people, there's no way I see a sample mean of 7'2", right? So taking a higher sample size will change the distribution of the sample means that we're looking at. Okay. So is there anything else that we can say about these distributions? Well, there actually is. So what ends up being true, if we have some random variable X that we sample from, so maybe this was income, right? That was the original X variable. It has its own population mean and its own variance. Right? So if I then look at my sample mean distribution, and let's say I have those 1,000 different sample means, when I calculate the mean of those 1,000 sample means, I actually end up finding whatever the population mean was of the data I sampled from. Right? So this would be the idea, something like this. Let's say I'm thinking about different values for my sample mean. Now, I know that so I'm telling you the mean of your sample means should be whatever the true population means. Let's assume, I don't know, we're looking at income. Let's say it's 55,000 just for now. Well, if I take a sample of, let's say, 50 people, even if the true mean is 55, from my sample, maybe I see something close to that, like 56,000. I take another sample, maybe I see 54. Take another sample, maybe I see 63. I take another sample, maybe I see, so 54 just below it, and 51, and then, I don't know, 59. I'm going to probably find values that are close to that mean, but they're going to deviate a little bit, right? If I'm just looking at any one sample, right? So if I take enough samples and then I take the mean of all these different samples, they should all be centered around whatever that true population mean was. But even if I can't observe it, I know that I should be seeing values that are kind of close to that mean. So they're trying to give a little bit of intuition. Obviously, like I'm not showing you mathematical proof, but hopefully when I show you some data and then we'll kind of look at this, I think that'll help kind of confirm or at least support what I'm saying here. Okay. What also ends up being true is that the variance of our sample mean distribution will be the variance of the original data we sampled from divided by our sample size. So this was the idea that if I take a sample of size 2, well, I could see some really extreme values, right? If I have one person in a sample size of 2 who makes $250,000, I'm going to see a sample mean that is greatly different than whatever the true population mean is. But if I take samples of size 100, that one person doesn't influence that sample mean as much. It's very unlikely over 100 people that I see like an average income of 150,000. You know, so kind of the idea there is, if we remember, my equation for the mean was to add up all the values divided by the number of numbers I had. But we actually said we could rewrite this something that looks like this. So notice the weight of every single observation is 1 over n. So if I take a higher sample size, what's going to happen to my weight? Well, actually, each observation is going to carry less weight, right? Because now instead of being 1 out of 2, it's 1 out of 100. Right? So as I take higher sample sizes, it's just less likely that I get kind of these extremely large or extremely small values. All right, so let's kind of set up here. And I kind of already alluded to this, but let's think about what's going to change the variance of my sample means. Right? If I've got the equation here, if the original variable has a higher variance, well, then my sample means will have a higher variance as well. Right? You can kind of prove this to yourself if you just take samples of size 1. If I take samples of size 1, well, then that was the idea that I could see a sample mean of $1 million, right? If I randomly select one person that happened to make $1 million, I could, you know, if I'm selecting one person, I could see somebody make $0, right? And so if I have samples of size 1, my distribution should really just be whatever the original variable was, right? If I'm just taking samples of size 1, which sure enough here, sample size 1, the variance of my sample means will just be whatever the variance of the original variable was. Now, as I take higher and higher sample sizes, right, it's not as likely I see these extremely high and low values. And so the range I'm getting is much narrower, or I'm getting a lower variance, right? Which that would play out here as well. If I take a higher sample size, the denominator is getting larger, the overall fraction would then be smaller. So higher sample sizes actually reduce the variance of my sample means, right? And the idea, kind of the intuition there is, right, I can't see these extremely high and low values when I take samples of size 100. I'm not going to see a sample mean of 150,000 for income. So those are, oh, and then kind of mentioning the standard deviation, once again, just like always, is just the square root of the variance. All right, so now we've got two things that are defining our sample mean distribution. Okay? Like I said, for now, you'll kind of just trust me that this occurs, and then I'll kind of show you with some data. Okay. All right, so, and don't worry about this. This is a rule that just says, like, if we have, that our sample shouldn't be too large in relationship to our population size. But, you know, we're usually dealing with population sizes that are very, very large. It's almost impossible to get kind of sample sizes that would be too large here. So I'll kind of give you an example and kind of just show you that, you know, the procedure, how we go through this, and then try to give a little more insight. So let's say I've got some original variable X, which is birth weight. All right, so I had every birth in Indiana in 2004. And I find the average birth weight, right, is 3,287. The variance is 360,000. If I take samples of size 36, so I randomly select 36 births, I calculate the sample mean birth weight for those 36 babies, write that number down. Randomly select another 36 births, calculate the sample mean birth weight for those babies, write that number down. I keep on doing this, right? So maybe I do it like 10,000 times. So 10,000 different sample means. What would the mean of those sample means be, and what would the variance be? So maybe I'll try to give a visual for this one to help make a little more sense. So this original variable x we started out with was centered around, what was it, 3,287, I think. And then it had a variance of 360,000. So our sample mean distribution, and for now, I'm going to draw it as normal. I'll kind of show you why that is, or tell you what conditions we need for that to be true in just a second. But it should be that the mean of my sample means ends up being exactly equal to whatever that population mean was of the variable I sampled from. The variance of my sample means is the original variance over my sample size. So I think I was taking what, 36 births. So this would be 10,000 here. Or if I wanted to find the standard deviation, square root of 10,000 should be 100. So that's kind of the visual, right? But if you want to just remember the rules, right? The mean of my sample means is always the original mean of the data I sampled from. And the variance of my sample means will be the original variance of the data I sampled from, however, divided by my sample size. This is just the idea that as I take a higher sample size, it's less likely I see extreme values, so I'm getting a much narrower variance. Any questions up to this point before we keep moving here? So I think what? This should be the answer to that question. So jumping ahead a little bit, I think I'll show you the slide, but the next slide, I believe, had something on there like, well, what if I take samples of size 100 instead of 36? So if that's the case, I didn't draw that this should go through the middle, but hopefully you can draw better than I can. The mean of those sample means, if I take a different sample size, should still just be the original mean of the data we sampled from. So the sample size doesn't change where our distribution of our sample means will be centered around. Every sample mean distribution is centered around whatever the original population mean of the variable we sampled from was. Okay. What is impacted by the sample size is going to be our variance or our standard deviation. So notice, if my sample size gets higher, what happens to my variance for my sample means? So if n goes from 36 to 100, dividing by a larger number should make it smaller. So I know that it should be less than 100. Now, if I go ahead and calculate it, right, another way we can write the standard deviation, it's just the square root of the variance, but my variance follows this equation here. So I could actually kind of think about writing it this way as well. Right? So the standard deviation of my sample means is just the square root of the variance, but I know that the variance is equal to this, the variance of my sample means, sorry, is equal to this equation. So that's why I just plug that in there. So from here, the square root of 360,000 over 100, which I think we should get what? 36,000, so 60. So sure enough, taking a higher sample size led to a lower standard deviation or a lower variance in my sample means. And that's the idea, as I take a higher and higher sample size, it's just less likely I'm seeing values that are further from the mean. If it's less likely I see values further from the mean, that means that my variance is lower. So any questions on these? Let me see, is there, that makes it worse. So I thought maybe the light was on. This looks a little bit light. So if you have any questions over everything I'm writing, make sure you ask. Everybody with me up to this point? So we can kind of understand that. Oops. We kind of worked through this one as well. We saw that the new variance is what, or new standard deviation was 60. Okay. So what's going on with this variance is we can think about, as I take higher sample sizes, right, I'm not going to see these values further from the mean. And so the variance goes down. So you kind of imagine just a nice little visual. You know, if I'm just starting out with my original variable X or samples of size 1, we can think about it as. If I then go to samples of size 5 and samples of size 50, notice that distribution is getting kind of more and more peaked. Or it's guaranteeing that the values around the mean are way more likely for us to see, and values further from the mean are becoming less likely. Okay. So it kind of just intuitively makes sense. If we have more observations, it should be that our sample mean is going to be a better or more accurate representation of whatever the true population mean is. So you think about why we're having this discussion or where we're kind of going is we're going to take a sample. That's the only sample mean that we're going to be able to see. So we want to understand the principles behind this distribution because we want to make sure that we can guarantee our sample mean is going to be close to whatever that true population mean is. We can't observe the population data usually. Right? All we have is our sample data. We talked about that last class. We use our sample data to make inferences about the population. So I want to try to guarantee that my sample mean, my sample statistic, is going to be close to whatever that true population statistic is. Okay? So that's why we like this idea of taking higher sample sizes, because if the variance is lower, that means that we're just less likely to see things that are further from whatever that true mean is. Okay? So another way to kind of look at this, I think it's worth kind of going through, is let's say I'm looking at my sample means, and we'll kind of use that previous example. So I had what? The original one was centered around 3,287, and it had a standard deviation of 100. So if I take a higher sample size, which led to, a standard deviation of 60, but it was still centered around the same value, right? It's just that it had a smaller variance. So what a smaller variance means that the distribution of sample means when my sample size was, I think here the sample size was 100, and here my sample size was 36. So I took a higher sample size, which led to a lower standard deviation, which means that values kind of around the mean have become more likely, and that values further from the mean are less likely when my variance is low. Right? So I'm getting a more peaked distribution, okay, which is good. If all I can see is one sample mean, now at least I know that that one sample mean has a higher likelihood of being close to the mean, lower likelihood of being further from it. Questions on that before we keep moving? Okay. So, oops, I had another visual here, just kind of showing, you know, even if I started out with a variable that's like, technically this is kind of uniformly distributed, but it's kind of noisy. So just kind of this flat line when sample size was 1. As I take higher and higher samples, the sample means start to become more and more peaked, right? We kind of said that changing the mean shifts it, changing the standard deviation of the variance makes it more peaked or flattens it. So this is just kind of another visualization of that. So I've been drawing these distributions as normally distributed, but why is it the case? So if I start out with a variable and I sample from that variable, so if that original variable is normally distributed, then my sample means will also be normally distributed. And they'll have a mean that is the same as whatever the original population mean is from the data we sample from. And the variance will be the original variance divided by our sample size. What if the original variable isn't normally distributed that we sample from? Well, there, we still know that the sample means will be normally distributed as long as we can guarantee a sample size over 30. Right? So this is called the central limit theorem. And basically, you can prove mathematically that if you can get a sample size over 30, it doesn't matter what the original distribution of the variable you sample from was. Once you get to a sample size over 30, it's approximately a normal distribution. It's not perfect, but it's so close that we say that we can treat it like it's a normal distribution at that point. And you know why this is? I mean, it kind of goes back to like, I guess I'm trying to give some intuition behind that. I would say it's kind of like the discussion I had of like, you know, whatever that true mean is, I'm going to start to see values that are kind of close to it. Sometimes I'll have samples that are a little bit skewed, but it's less likely I get samples out here. And so just kind of by the nature of taking these samples, it happens to be that once I get large enough samples, the values I see end up being normally distributed. Right? And this is just a nice byproduct. Now, for now, you're taking me at my word because I haven't showed you the mathematical proof, but I'll kind of show you the data here in just a second. So if we can get a sample size over 30, we also know our sample means will be normally distributed. Right? And as we take higher and higher samples, it just becomes closer and closer of an approximation. After 30, we say it's close enough, but really, as we take higher samples, it will just become more and more close to a normal distribution. So this is always, I kind of like that. Sometimes I steal some things from different books. I always kind of like this graphic, which shows, you've got 4 different variables starting out. They're all very different distributions. And if you take samples of size 2 and then graph the sample means, they don't really look like much. These are kind of weird looking, right? At sample size 6, some of them already start to look like they're normally distributed, right? And centered around whatever the original mean was. Here, these are still a little bit skewed. But once you get to 30, all of these are normally distributed. Right? So let's take a look at some actual data and see if this holds up. I mean, I could have drawn this out and this could be completely false, right? So I had some old Indiana birth data, right, from 2004. So it's about 87,000 births. So I had 4 variables, right? Birth weight, length of the pregnancy or gestation, this health score, this APGAR score is a measure of like the baby's health, and then whether or not the mother smoked while pregnant. Right? So that was just a 1-0 variable. So for each of these, I had this data. I calculated the mean and the variance, actually not variance, the mean and the standard deviation of this original, these original 4 variables. So, the mean birth weight is about 3,287. Length of pregnancy is about 39 weeks. About 18%, right, or a proportion of 0.18 of mothers smoked at some point during the pregnancy, which seemed to me to be alarmingly high, but I don't know, it's about 15 years ago, so maybe trends have changed, right? And then most babies are born fairly healthy in the US, and so you see a lot of 8s and 9s here for this health measure. And then I've got their associated standard deviations. So if we look at these variables, right, birth weight starts out normally distributed. This is like just one of these biometric or one of these biometric measures that follows a normal distribution. It just happens to. The length of the pregnancy kind of has this long left tail. I think we've looked at this maybe distribution before, right? You can see premature births, but we don't see babies born at like 11 months. Right? So we got a long left tail, not normally distributed. This health measure, definitely not normally distributed. In fact, it has a huge mass right at 9. And then I didn't put it up here, but what would the maternal smoking kind of variable look like? Well, that was just a 1 or 0. So it'd be a bar that goes up to 0.18 for 1, right? That was people who smoked or pregnant, and then 0.82 for the 0 for the people who didn't smoke, right? So that one definitely starts out not even as a normal distribution. In fact, that one's not even a continuous variable. But this is kind of nice. It doesn't matter if the original variable is continuous or not. When we're looking at the sample means are continuous, right? If I take samples, I could see anything between 0 and 1 for the proportion of mothers who smoke while pregnant, right? Right, depending on my sample size, right? I'm going to have different intervals, but if we're thinking about I could choose any sample size, then what are the possible values for me to see as my sample mean for maternal smoking? I could see anything between 0 and 1, right? And so my sample means are continuous random variables. So even if the original variable that we're sampling from isn't, my sample means will be continuous. So that's kind of becomes important. Now, if I take samples here, so let's say I randomly select 100 births, and I want to think about what's the distribution of the sample means for these 100 births going to look like. So I take a sample of 100, I calculate the sample mean birth weight, sample mean gestation, APGAR score, maternal smoke. I randomly select another 100 births, calculate the sample mean birth weight, gestation, etc. I'm writing these down, like storing them in an Excel file. I do this 1,000 different times. Well, if I have 4 columns of data that just represent the 4 different variables and the 1,000 different sample means I calculated for each variable, well, in Excel, I very easily could then find the mean of those sample means using the average function, could find the variance of those sample means, right? And I could even graph out the distribution of those 1,000 different sample means. So that's what I'm going to do. Now, if what I'm telling you is true, it should be that when I calculate the mean of these sample means, they should just be those original population mean values that we found. So the 3,287 for birth weight, the 0.18 for maternal smoking, et cetera. The standard deviation, if I write out the equation for the standard deviation, it's just the square root of the original variance divided by my sample size. So here, if I'm taking samples of size 100, the square root of something squared cancels. Plug in my n. What I really end up with is that the standard deviation of my sample means should be the original standard deviation divided by 10, or the decimal point should just get moved one place, if I'm taking samples of size 100. So let's look at if they were. So I actually did this. So I had these 1,000 different sample means in an Excel file. I then calculated the mean of the sample means and the standard deviation. So here was the original data. Here's the mean of my sample means that I calculated. Notice almost exactly the same as the original population means. Now they're a little bit off, right? Some of these are a little bit off, but that's because I only took 1,000 different samples. To really get it to be perfect, I'd need an infinite number, right? The actual mathematical proof is saying any sample mean that you can see. So you could have an infinite number of sample means to really prove the actual mathematical proof, right? But you get close enough here, at least, I think that really supports and gives pretty good evidence that, yeah, this is holding, right? The mean of my sample means ends up being just whatever the original mean of the data was. And now here it gets a little weird because I'm rounding things to the second decimal, but all the original standard deviations we said should be, the standard deviations of our sample mean should just be the original standard deviation divided by 10, or move the decimal one place. Sure enough, 600 becomes 60, 2.66 becomes 0.27. If we looked out a little bit more, I think this is actually like 0.268. So it's still a little bit off, but it looks like it's off by more because I'm rounding the second decimal here. 0.38, the decimal should get moved one place. So 0.038, we get about 0.04. Once again, rounding the second decimal. So it was actually even a little bit closer than that. And then 0.82 should become 0.082. And we get about 0.08. So we're a little bit off here, right? But that's because, like I said, it's only 1,000 samples as opposed to an infinite number. But even though we're a little bit off, hopefully you can kind of see like this is really, really close to what I was telling you is true, right? So this will hold. It's just that I was only using 1,000 samples. I guess I was lazy. I could have done like 10,000. It just would have taken a lot longer, right? So is this making sense? Are there any questions up to this point? Now, I also told you that no matter what the original variables started out distributed as, the sample mean distributions, which should all be normally distributed. So then I kind of took each one of these variables and like did a histogram, right? So for birth weight, I mean, this follows a perfect normal distribution, but the original variable is normally distributed, so we shouldn't be too surprised, right? Now you'll notice if we look at the original variable, or we could think about it almost like samples of size 1, like one person, we could see some extremely low values. We saw some pretty high values up here. When I look at the sample mean, it's very unlikely across 100 births that I'm going to see, you know, the average birth weight be that of a premature baby of like 1,000, 1,500 grams. And in fact, the sample means I see are within a much smaller range, right? And that's the idea because they have the original variance of the data we sampled from, but divided by the sample size. So we're always going to have a lower variance for our sample means than the original variable itself, or kind of lower variance translates to like a narrower range of values. Okay. Oh, I'm going all over the place here. Let me use my arrows instead of my mouse, apparently. The length of the pregnancy, that one started out with a long left skew. Notice the sample means really close. I mean, this looks like a perfect normal distribution. The APGAR score, pretty close to a perfect normal distribution. And maternal smoking, you could argue maybe it's a little bit off, but you can kind of imagine like it's pretty close to normally distributed. Now here, this one would really get helped out if I took more than 1,000 samples. So if I had like 10,000 samples here, this would be a lot more precise. Right now, this is definitely showing that we're saying they aren't perfectly normal distributed once we take sample sizes over 30. We're just saying they're approximately, right? They're close enough for us to be able to use it to calculate different probabilities. So what's this discussion leading to, right? So we're trying to get all these characteristics about the distribution of sample means out there, because once we know they're normally distributed and we can determine the variance and the mean, we can start to do things like, well, I can convert this normal distribution into a standard normal distribution and find the probability I'm above or below certain values. So a little bit of an aside here. So I'll kind of allude to something and we'll return to the slides. So let's say I've got my distribution of my sample means, right? And I make sure that the sample size is over 30. So it follows this nice normal distribution. I've got the mean of my sample means, which is just the population mean. And I know that the variance of my sample means is the original variance of the data I sampled from over my sample size. And we could write out the standard deviation, which would just be the square root of that. Okay. So that's the distribution of my sample means. Let's say now I'm interested in something like this. Well, what's the probability I see the sample mean take on a certain value or anything below it? Well, this should look really familiar. If I can convert that value into a z-score, once I have that z-score, I can just look that up in the table and it'll give me that area to the left of the probability that I wanted. Now the question becomes, how do I calculate that z-score? Right? So we had all this discussion. Now that we know the sample means are normally distributed, we can start to find the probability the sample mean takes on certain values. So before, when we were thinking about some variable x, this is how we calculated our z-score, right? Or converted that x value into a z-score. What we're now going to be looking at, we're turning a sample mean value into a z-score. So we're no longer going to be taking cutoff values for x. We're looking at cutoff values for x bar, or for our sample mean. So the z-score, you take whatever the statistic you're interested in. Now, originally, the statistic that we were looking at was just the variable itself. Now, we're looking at the statistic of the sample mean. So we're thinking about the distribution of sample means. We'll subtract the mean of our sample means and divide by the standard deviation of our sample mean. So same setup, it's just that we've got to make sure we're using the mean of the statistic that we're interested in and the standard deviation of the statistic we're interested in. And then from here, well, the mean of my sample means is always just my population mean. And the standard deviation of my sample means will always be square root of my variance of the original data I sampled from over my sample size. Okay. So because we knew all these things about the distribution of our sample means, we now have the information that we need to be able to turn different values into z-scores and find the probability that we see a sample mean above, below, or between certain values. Okay? Like once we get this z-score, all the same steps that we were doing before apply, right? Once we get a z-score, I can look it up in the table. You know, if I want the area to the right, I might have to subtract it from 1, but it's going to look identical to what we were doing once we get to that, calculate that z-score. So all the steps 3 and 4 here, this is exactly what we were doing before. Step 2 is really also the same. It's just that our z-score equation was a little bit different now. And I wrote this a little bit differently than I think I did on the dot cam. So here, I'll kind of show you 2 different ways of this. So this denominator, which represents, right, the standard deviation of my sample means, I could rewrite it like this. And it means the exact same thing, just writing it a little bit differently mathematically. And that, which one's easier kind of depends on what information I've been given. Right? But other than that, calculating the z-score, all of our steps are the same with the added step of we need to make sure we have a sample size over 30. Okay? Any questions up to this point? All right, so let's go ahead here. So let's go through an example here real quick. So let's say I've got some original variable x, and it's got a mean of 5, variance of 2,500. I take samples of size 100, and I want to find the probability I'm in between 10 and 15. Okay? So we'll kind of set this one up. So we've got this original variable x, which represents just some continuous random variable, and sorry, just x. Right? And I know that the mean is 5, and the variance on this variable is 2,500. Okay. I then take samples of size 100, and I want to think about what's the distribution of those sample means of size 100. Well, they should be centered around whatever the original mean of the data I sampled from was. So they should also have a mean of 5. And then the variance should just be the original variance over my sample size. So 2,500 over 100 or 25, which means that the standard deviation is just the square root of that or 5. Okay. So that was just taking what I knew about the original x variable and thinking about, okay, now with that information, what do I know about the distribution of sample means? The next question was, what's the probability we see the sample mean value somewhere between 10 and 15? Okay. Well, I want to find that probability. I can convert these into z values. I could then look up this z value in the table, find the area to the left of it. Look up this z value in the table, find the area to the left of it. If I subtract the smaller from the larger one, I'm left with what's in between. Okay. So if I can get these z-scores, it looks like very similar to a problem we've already done. Now this one, I use some easy numbers to make a point. So how far away is 10 from 5? 5 away. My standard deviation is 5. What should that z-score for 10 be? Remember the z-score, yeah, still represents the number of standard deviations away. So if I'm 5 away and the standard deviation is 5, I'm 1 standard deviation away from the mean. How far away from the mean is 15? 10, which is 2 standard deviations. So my z-score there would be 2. Now I could go through the process, right? So if I want to calculate my z-score, I'll take that value of 15, subtract the mean, which was 5, and then divide by the standard deviation of my sample means, which was 5. Sure enough, I end up with that z-score of 2. Okay. Well, now this should look very similar to something that we've already done. We actually literally worked through a problem where the standard deviations worked out to be exactly 1 and 2 as well. So we would go to the table. The area to the left of 1, that z-score of 1 is 0.8413. Area to the left of the z-score of 2 is 0.9772. So really all that's left to do, right, is take that smaller area, subtract it from this larger blue area. That bricked area would kind of cancel out everything here, and I'd be left with just what's in between them, which is at 0.1359. So once we calculated those z-scores, the steps were exactly the same. I mean, this is exactly the same process that we worked through an earlier problem with, right? It's just that to get those z-scores, it's a little bit different now. Right? But once I determine what the standard deviation is of my sample means, like especially if the numbers are nice, it still can be kind of easy to imagine how many standard deviations away you are, especially if the numbers are as clean as this. Okay. Any questions over that before we keep moving here? Is this making sense how I'm kind of relating to the old stuff? And, I know it's relatively new as well. But I think, once we can get that z-score, it's really the same as the processes that we have been using. So let's do another one. I think this one's just to kind of reiterate. So try to put this, there we go. So let's just think about the original variable that we're sampling from here, which is the length of the pregnancy. So we got our original variable x. I don't know, I think it had a little bit more of a skew to it here, but the main important part is it doesn't matter how it started out, right? So I guess technically I could think about this as, try to draw it a little more accurate. So this was like something like this, right? So these extremely low values were pulling the mean down, but the mean was about 39 weeks. And then the variance was 9. So I want to know that if I take samples of size 81, what's the probability that I see a sample mean above 39.5? Okay. So here, I'm going to try to draw this straight. If I think about the distribution of my sample means, they should be normally distributed. And the mean of my sample means should be whatever the mean of the original data I sampled from was. Okay. The variance of my sample means is the original variance of the data I sampled from over my sample size. So here that's what, 9 over 81 or 1/9. If I want the standard deviation, that's going to be the square root of my variance, or about 1/3. So I've got my distribution for my sample means. I'm now interested in what's the probability I see the sample mean take on a value of 39.5 or anything greater. Okay. So the final step is, now that I know what I'm looking for, turn this value of 39.5 into a z-value. Right? I can then look that up in the table. It'll tell me the area to the left. I wanted the area to the right, so I would need to subtract it from 1. Now, if I'm just trying to like envision, like I'm what, 0.5 away from the mean here. 39.5 is 0.5 away from the mean. If my standard deviation is 1/3, well, I'm more than one. I might not be good at math, but I'm more than one standard deviation away, right? So I know my z-score is going to be above 1. But also, if I think about it this way, what do I know that this probability has to be less than? Yeah, the area to the left and the right of the mean is 0.5. So if I want the area to the right of 39.5, that's going to be something smaller than 0.5. But, other than that, I have to actually just work it out. So we'll calculate that z-score, which is take that value you're interested in of 39.5, subtract the mean of 39. And then here, it's kind of a shortcut, but not really. I could write this out. So I could, I'll use this sheet to kind of show you. I could do 39.5 minus 39 divided by the square root of, what was the original variance? 9 over 81. Right? So that's kind of using the longer form version. So that's just plugging everything into this equation. But notice my denominator just represents the standard deviation of my sample means. So if instead I already had the standard deviation of my sample means, instead of plugging in the square root of 9 over 81, I found earlier this was just 1/3, right? So I could just plug into the denominator here, whatever that standard deviation of my sample means actually is. Now, if that confuses you, it's fine to just always default to this equation, right? But if you've already got the standard deviation, it's a lot easier to just plug that one number in there. Right? Standard deviation of your sample means. So if I do this, I think I end up with what, 1.5 here as my z-score. From there, I just go to my standard normal distribution table. I look up 1.5, and if I remember, this is 0, so 1.50, 0.9332 would be the area to the left. I wanted the area to the right, so I just subtract that from 1. And sure enough, I get something that's less than 0.5, quite a bit less than 0.5 actually. Any questions over anything in that process? Hopefully, like this kind of stuff is looking similar. Like we've already really done this. It's just calculating that z-score, which is kind of the new wrinkle. Right? One thing I also want to point out here. So when we think about these z-scores, it's the number of standard deviations away from the mean we are. So notice, I shouldn't like jump to any conclusions. Like when I said, okay, this has to be less than 0.5, you might look at this and say, yeah, well, but 39.5 is really close to 39. So this area should be yeah, it's a little bit less than 0.5, but it'll be really close to 0.5. But then when you actually calculate it, it's 0.06. So why did that happen? Well, because even values for our sample mean that aren't very far from the true population mean, if our standard deviation is low, that could be a lot of standard deviation. So for instance, even if I'm 0.5 away, if my standard deviation was 0.1, that's 5 standard deviations away from the mean. So just because the values for the sample mean are close, don't think that that tells you anything about the probability. What you're really concerned with is that Z value, right? The number of standard deviations away that it is from the mean. So you can imagine, like for income, you know, the same distance of 0.5, well, that's like a fraction of a standard deviation for income. So it all depends on kind of what variable we're looking at. So don't just look at the distance to that sample mean from whatever value you're interested in. Think about how many standard deviations away it is, right? And if the standard deviation is low, being 0.5 away, you end up being 1.5 standard deviations away. Any questions on that? Okay with this? So we probably won't do any Excel stuff until after spring break when it comes to like the sample means, but you can imagine like really everything we've done up to this point, it'll look very similar, like how we would do this in Excel. The only real difference is going to be in calculating those Z-scores. It's just going to be a slightly different equation. Okay? Other than that, like once we have the Z-scores, all the formulas will work the same, and we should be pretty good to go. Okay? I think Friday, maybe we'll take a glimpse at Excel. I don't think we'll probably get there. I'll probably work through some more problems thinking about the distribution of sample means and how we can use that to do things like confidence intervals and hypothesis testing. Okay. So those two that connect assignment and the Excel assignment are currently up there. I would suggest working on them, try to get as much done as you can, given the material we've covered. That way, you know, you can kind of take a break over spring break, and then we can kind of come back to things there after a week. Okay. All right. If you didn't get your exam last class, I've got them with me. So if you want to get on the way out, just let me know. Other than that, otherwise, I will see you guys on Friday.